Hello, everybody, and welcome to We Measure the World, a podcast produced by scientists for scientists.
You asked earlier, what are the ramifications when we fail as geotechnical engineers? And I think there's the traditional failure. Okay, yes, if we have a bridge foundation fail and the bridge collapses, that's catastrophic in one way. But as we advance in society and we change our dependence, especially on electricity and data centers, that failure can look completely different. And one of the things that we do in Terracon and what we exclusively work with Meter for is measuring thermal resistivity, and that gets tied into these data center and these solar projects. So failure can now look completely different than what it's looked like traditionally in the past.
That's just a small taste of what we have in store for you today. We Measure the World explores interesting environmental research trends, how scientists are solving research issues, and what tools are helping them better understand measurements across the entire soil-plant atmosphere continuum. Today's guests are Matt Ridgway and Dr. Arash Hosseini. Arash is a geotechnical and pavement engineer with extensive academic and industry experience in soil and asphalt mechanics, numerical modeling, and data-driven analytics. He's earned master's degrees from Sharif University of Technology in Iran and the Colorado School of Mines, and his Ph.D. in pavement engineering from Temple University. He currently works in Terracon's business transformation group, where he supports initiatives that integrate historical data and advanced numerical methods to enhance the quality and efficiency of geotechnical services at Terracon. Arash has authored over 25 peer-reviewed papers and is a frequent presenter on topics including pavement performance and geotechnical analytics. Matt Ridgway is a licensed professional engineer with a background in geotechnical and mining engineering. He currently serves as Assistant National Manager at Terracon, where he focuses on standardizing processes and developing new methodologies, particularly in the renewable energy and digital infrastructure sectors. He holds Bachelor of Science degrees in Civil Engineering and in Mining Engineering from West Virginia University, and maintains licensure in over a dozen states. His expertise includes field exploration, foundations, geostructures, slope stabilization, instrumentation, and mine mitigation design. And today they're here to talk to us about strategic partnerships and innovation in geotechnical engineering through standardization, data accuracy, and evolving industry practices. So, Arash and Matt, thank you so much for being here.
Thanks for having us.
Thanks for having us.
So today we wanted to talk about the work that Terracon is involved with. But first, can you tell us a little bit about your backgrounds and what initially led you to geotechnical engineering? So, Matt, why don't we start with you?
So I probably follow a little bit different background than most. I actually went to the University of Arkansas when I graduated high school and was studying business. Was wrapping up business school in 2008 and realized I needed to actually have a degree that had a marketable value to it. So I went back and went to engineering school. So taking that business approach, I decided that looking at the different engineering, I had a lot of interest in what civil engineering was, and quite frankly, I just grew up in a small town in rural Arkansas, and I had no idea what a civil engineer actually was. And started exploring into it, thought it looked interesting. And then as I got farther down to it, sitting behind a computer 40 hours a week wasn't for me. Geotech's a great place where you get a little bit of field work, get to see outside. You're involved in all the different projects. And then you also have a little bit of recession-proof segments to being in geotechnical engineering. When the economy is great, private developers are building everywhere. They touch the ground. When the economy is bad, you got public work, infrastructure money being spent. Everything built ever has to touch the ground. So geotech is probably the most advantageous from that point of view. And that's where I found myself here today.
Great. And Arash, how about you?
Yeah, similar to Matthew, started as a civil engineer and got fascinated by the complexity associated with geotechnical engineering and actually complexity of geomaterials, different phases of solid, liquid, air makes a really interesting interaction and interesting mechanic for these materials, which also offers a lot of opportunity to grow and learn and push the science forward in that realm. So after getting my master, I started doing PhD on yet another interesting material, which is pavement and asphalt. which has everything that soil has, but also on top of that has a viscoelastic behavior and has the time and temperature impacting the behavior of the material. And then after I finished my PhD, I joined Terracon and been with Terracon for the last 5.5 years, working on different projects on geodesign, geotechnical engineering, and also some of our data products. Yeah, as I said, it's just interesting to see geotechnical engineering as a young discipline of science, how fast it is evolving and how much unknowns are out there that we can dig into that and improve our understanding of these materials.
Yeah. Yeah, we definitely want to get into that in this discussion as well. Matt, could you tell us a little bit about your current role at Terracon?
Like Arash, I went to school, started off with civil engineering, then I got into geotech. Having a little bit of the business background from business school, I found myself in management fairly early on in my career, and I've been managing departments and groups for about a decade now. And what I found myself doing is getting into where a lot of management is not telling people where to go or what to do, but it's about understanding the processes and optimizing them. And that type of mindset was a little bit different than a lot of my peers I think had, which is more of a technical, just look at, hey, here's the job, here's how to do it, and just go do it the way it's always been done. So I came in to manage the pilot load testing operations that Terracon had grown over the past decade or so. With they have some tremendous leadership here that was forward thinking, but we also had a lot of growth very rapidly in the pilot load testing with the solar fields and the work that is supporting that. So what ended up happening is they grew so fast, it was such a big business line. They wanted someone to come in and help make sure everybody was operationally doing it correctly, but also had the understanding from the background and the science and knew the engineering behind what we were doing. So that's where I came into Terracon, was to help with the pilot load testing. And then at a previous employer, I had started working with thermal resistivity, which is something that we had not seen in the industry as a very common test prior to 2015 or so. You would see it as a one off and it was done here and there, but it wasn't something that was very commonplace. And I got involved with that. Just kind of funny timing sometimes. Was in a car with my boss and he got a call and someone was asking questions about thermal resistivity. And then when he got off the call, he's like, who do we know that knows anything about this? And I piped up and said, hey, I've got some experience. And now I found myself also leading the thermal group within Terracon.
So before we dive more into Terracon and what it's trying to do and what it's working on nowadays, I thought it'd be good to take kind of a step back, take an overview of geotechnical engineering as a whole. We haven't had too many geotechnical engineers on the podcast. My assumption is that a good chunk of our audience are not geotechnical engineers as well. So if you could just take a quick second and just kind of give us a brief overview of what all is involved with geotechnical engineering, its association with civil engineering, its relationship between the two, and then we can go on from there. So Matt, why don't you keep going with that one?
Yeah, so geotechnical engineering is the engineering side of looking at the earth and how it interacts with forces and loads and the development that is put on it. You know, as Arash was saying earlier, there's different soil types that we have, and everybody calls it dirt. But if you pick up a handful of, and I'm going to use this word sacrilegiously, dirt out of the ground, you don't just have soil in your hand. If you look at that in the container, there's water that's part of that. There's air in that, and all of those different parameters come in together, and they act differently based off of so many other outside external forces, such as what the climate and the environment is like, where it's located, what the clay percentage is, what the sand percentage is. So it's much more than just dirt, and understanding how that is going to react when you load it is really the basis of what geotechnical engineering is. One of the things that I really enjoy doing, I have spent some time working on some forensic projects, and I got to do one of the largest landslides in recent U.S. history from a forensic standpoint, and I loved it, is it's not always a clear-cut answer. When you start looking at designing roads or designing sanitary systems, there's manuals, there's guides. It's go look it up and apply it. Now there's still some problem solving in there. It's not something that you can do just with a computer. But contrast that with geotechnical engineering. And the reason you see geotechnical firms that tend to be very regionalized, and even when Terracon, the way we adapt for being a national firm and making sure we get good data is that regional knowledge you get. I can go tell you everything within 100 miles of where I live. I can give you a good idea of what the soil types are, what the problems we have are, and how that's going to affect the projects. Now, to go put me in North Dakota, I can't even tell you what the soil type in North Dakota is. So it really makes each problem or each project a problem where we have to actively think, and it becomes more problem solving and forward looking, and risk management and mitigation all becomes part of it, because we are the only form of engineering, maybe minus biomedical, where we don't control everything. If you go design a rocket ship, you control every nut, every bolt, you control every aspect of what your design is. We are placed with what's been there for billions of years whenever the earth has been formed and what has happened to it since, and it's in the ground. And then we go out and, on a truly analytical standpoint, we take somewhere between 1/2 to 1% of data from a site on a small site, and it's even smaller usually on larger sites. And then we have to make educated guesses about what really is going on over the entirety of that site based off of our background. So that problem solving aspect is something that unique, I think, to geotech, not where it's not that every engineering doesn't have problem solving, but it becomes a lot more experienced and judgment based than it is go look it up in a textbook or run a calculation.
Yeah, geotechnical engineering is a branch of science that investigates the response of soil to mechanical and environmental loading. So we as geotechnical engineers investigate the properties of the soil, mechanical, hydraulical, chemical properties of the soil, and we design our infrastructures based on our understanding of these materials so that we can have roads, dams, levees, structures, buildings, and knowing the response of the soil and rock to those external forces. Yeah, as Matt said, the complexity here is not just the mechanic of it is very complicated and complex, but also, unlike many other engineering disciplines, the soil and rock are not man-made products, so we have little control over what is out there, and therefore part of our job is to understand the properties of these materials and then design structures based on that understanding of the materials. And that's where meter is a great help for what we're doing, because meter group products are helping us to achieve that, to better understand the properties of these materials.
With all that being said, I really want to kind of focus in on the importance of geotechnical engineering. I think it'd be interesting to talk about just really quickly, what are some of the potential consequences if if your work isn't done right? Even, talking about the environment, or especially when it comes to safety risks and mitigation.
I think one example I mentioned earlier, I got to work on the forensics of a landslide. It was actually at an airport, and it was a large landslide. It went down, it dammed up a creek, it wiped out some houses, it caused flooding. That's kind of a best case, worst case scenario, because we do touch everything in the civil engineering world. If a foundation isn't designed correctly, it can collapse a bridge. If you see it, I think San Francisco, I can't remember the name of the tower, where they had some foundation issues and a very large skyscraper was leaning. I think probably the most famous case, something going wrong, but before our discipline was even really defined, was the Leaning Tower of Pisa. So I think that's some of the things, obviously, like you said, there's financial risk, but best case scenario, a landslide happens in the middle of a hill out in the middle of a farm field in Ohio, and someone just has to go clean it up or it just gets left alone. And those are the ones that are more common. But worst case scenario, we absolutely can get to where failures have real consequences.
If we don't do our job right, it may come with really significant consequences of risk of life loss as a result of failure of our infrastructures. Everything that we build above the ground is one way or another is supported by the soil and rock underneath that. So we need to understand the behavior and response of those materials. Otherwise, if that structure fails, or if we don't do our job right to design a foundation, to design a pile, or to design a slope, then that means failure of those structures and would be a catastrophic failure.
You asked earlier, what are the ramifications when we fail as geotechnical engineers? And I think there's the traditional failure. Okay, yes, if we have a bridge foundation fail and the bridge collapses, that's catastrophic in one way. But as we advance in society and we change our dependence, especially on electricity and data centers, that failure can look completely different. And one of the things that we do in Terracon and what we exclusively work with Meter for is measuring thermal resistivity, and that gets tied into these data center and these solar projects. So failure can now look completely different than what it's looked like traditionally in the past. Instead of failure just being a bridge that collapses, maybe it's a mismeasured thermal value and that leads to an undersized cable that melts that completely takes a data center offline or takes a solar grid offline. And then if that happens, then we can have downstream effects. It could be a first domino effect, especially on the grid side. So yeah, I think just because failure's always looked one way in the past, failure in the future can also look different because what we're doing as geotechnical consultants change. Like I said, this thermal testing is still relatively new as a commonplace in the geotechnical field. And, we haven't seen a lot of these failures happen yet, but when they inevitably will happen down the road, I think it's going to have maybe some more dire consequences than people anticipate.
I guess as a transition to get into what you're doing there at Terracon, how has the industry evolved in recent years? How have you seen that changed in the time? I guess even just the amount of time that you both have been working within that field.
Yeah, so being relatively newer in this field compared to Matt. But it's still, I'm seeing an ever-changing environment in terms of improving our understanding of the science behind the matter, and also application of that science in the state of practice. Geotechnical engineering used to be on paper and pen with a bunch of rule of thumbs and a lot of empirical, correlations as a result of limited number of tests. And then it evolved into more investigations in better understanding the soil materials, and also learning from other associated disciplines and importing them into our geotechnical practices and advancements in the testing equipments. We moved into automated machines in laboratory inside investigations. And now we are at the age of all this AI and the explosion in the computation power that we have at our hand, that can help us to better grasp this complicated interaction of different things in the soil and be able to understand it a little bit better. So it's keep evolving. As I said, it's a young discipline, been around maybe for about 100 years or so, but we learned and we evolved from there, and we keep evolving. This is, I think, one of the disciplines that has a lot of room for growth, and especially with the new technologies out there, we keep trying to improve our understanding and our methods.
So for listeners who may not be familiar, can you give us a quick overview of Terracon and the scope of your work?
So Terracon is a geotechnical, environmental, and material testing consultant company, has over 170 offices across the United States and more than 7,500 employees, and is more than 140 labs that keep testing properties of the soil in situ or on our field testing or in the lab. And also we work with a lot of outside labs to measure different soil properties, which makes us not only, I'm not sure if we are the biggest company, geotechnical consultant company in the country, but we are definitely one of the biggest ones, and perhaps one of the big companies in the world. So as Matt said, because of the massive operation that we have, we feel responsible for advancing in technology and adopting better ways of doing geotechnical engineering, because we feel that everyone else is also watching us and is counting on us to improve this profession of geotechnical engineering. So, and we are, all our works are on wide array of different type of projects: transportation, energy sector, commercial, retail, all these different disciplines. We are working as a geotechnical consultant, providing them design values for designing their foundations, pavements, and slopes, and etc.
Matt, what have you seen in your time in the way the industry has evolved?
So I think Arash alluded to it earlier, and I wanted to pull back is the fundamental testing that we use. People would first off be surprised with how rudimentary some of the testing we have is, and it is taken a semi spherical cup, digging a groove in it, and just hitting that cup routinely to see how quickly it closes. Things like that you would think in today's day and age we would have evolved. But even that, as simple as that is, that's only 115 years old. That's something that this science is so new. And to Arash's point, things are always evolving. And it's partly better technology allows us the opportunity. Part of it is we also have to adapt as a industry to what is actually going on in real life in terms of labor. A lot of what we do, we got to go out in the field and we have to send people on drill rigs, or we have to send people with excavators out in the field to do digging and recover samples that we use for this laboratory analysis. And when we have constrictions in the labor market, we don't necessarily have people that want to go do those jobs. They're hard, they're strenuous. And now we have to think of other ways to collect data that is going to get us where we need to go and isn't so reliant upon having, someone in the field running a drill rig for 13 hours a day out in Arizona, where it just is hard. So I think those types of constraints are forcing us to adapt and evolve new and better ways of doing things. And the other component, like I said, as the technology increases, our ability to measure bigger areas. I think, when I alluded earlier to saying we go out and get between 0.5% and 1% of the data on a site. If you think about purely what we're doing, we might go to a 2-acre site that's going to be a, name your favorite national food chain, and we're going to drill 6 holes in the ground that are 4 to 6 inches in diameter and 15 to 20 feet deep. And that's all we're going to get in terms of area. So now, if we have these technologies that allow us to see a bigger swath, maybe there's a clay vein somewhere that's going to be expansive and give us issues. Maybe there's a pocket of water. So newer technologies like geophysics are getting better, and that's tremendously changing the way our data collection looks like, and it's also giving us more information to design from. And I think, one of the things that is unique to Terracon and the way we are set up, we are a very, very large geotechnical firm that has worked all over the country, and we have done a really good job of retaining our data and digitizing that data. So we have a unique advantage to take and leverage all that data we have to do AI learning and then do predictive analyses. Whereas maybe a smaller regional firm, they might be able to do it just in that region, but for us to do it on a national scale, Terracon doesn't just have an obligation because of our size. We don't just have an obligation to lead this change, but we have a responsibility to the industry. That is where Terracon is really taking the lead and taking the bull by the horns to lead this change in industry to make sure that we can do a good job of improving a very rapidly developing science.
Also, add to what Matthew said, geotechnical engineering is also one important aspect of it is it's a very pragmatic field. We never stop building. We keep building, structures on the ground despite all these advancements that keep happening in the field of geotechnical engineering. But these advancements are making us to be safer, to be more accurate, and be faster. The geotechnical engineering that used to take maybe months or 5 6 weeks now takes 2 weeks 3 weeks, and we keep advancing in that front of making things more accurate, safer, and less costly by improving our understanding of the thing. So as I said, it's a very pragmatic. So we learned our way to put ourselves in the safest spot. But if we know more about the soil, then it's a matter of optimizing our design while keeping us on the safest spot.
So you've recently standardized equipment across your thermal labs. Can you give us a little bit of background about what that involves? What was the catalyst for that? I guess we should start with that. What triggered that to make you think that you needed to work on improving that process, I guess I should say, and innovating in that way?
So I think it starts with when we started doing the thermal testing, we only had about 12 labs that were doing it, and they had each grown organically to start doing it. There was not a system-wide implementation across the company to say, hey, these labs are going to do it and this is how it's going to be done. So the inevitable problem that you have is eventually you're going to get a bad test result somewhere. And when that happens, you got to start backtracking to figure out what caused it to go wrong and how do you remediate that. To that extent, when you have multiple labs using different pieces of equipment, now not only do you have to understand what went wrong once, you've got to relearn that process. So from a pure process standpoint, it just makes sense to have everybody operating the same equipment. That way, hey, we found an error because of this machine did this and this is what triggered it. Now we can now tell everyone, hey, don't do this because it will cause this effect. Or if we find something that is just a fluke, in a readout and maybe it's not reading properly, we know we can adjust our reporting system to account for that. So that was one of the aspects. We also changed the way we were reporting the data. And reporting the data, we wanted to have everybody with the same output files, back to just efficiency and not having to go relearn the whole process and have different processes for different pieces of equipment. So that's what really led trying to get everybody onto the same tools, because when everybody's using the same tools, when something goes wrong, that eliminates one of the different sets of problems you've got to go identify.
Also, add to Matthew, why do we even as a geotechnical engineers care about thermal resistivity? Thermal resistivity is measuring how heat flows in the soil. And we need to know that properties for a lot of different reasons, but one of the important ones is to design cables. And when we design cables, the failure criteria for designing cables is burnout of the cables. So we need to know the thermal properties of the soil, therefore we be able to design the cable for. Also on geothermal systems, also for understanding the add freeze and the depth of frost in the soil, because if you know the thermal conductivity of the soil, then you can calculate and know how deep would be the frost, or how would be the response of the soil to the change in temperature above the ground and below the ground. So a lot of different design applications for thermal resistivity, and therefore we need to be able to make sure that we know how to measure this, and our measurements are representative of the soil, are accurate, are consistent. Therefore, when we design something like a cable or a foundation under frozen condition or a geothermal system, that design is reliable and is based on real, good, accurate measurements of the soil. which led to all that effort that Matthew just described.
With that, the importance of thermal resistivity as a measurement, what led you to seek out Meter Group and be able to involve them in helping standardize your instrumentation there in your labs?
Meter had a unique advantage. They were one of only two companies that were readily making this product available. So we had both of those companies' products in-house. Some offices were using meters, ones was using the competitors. And it simply came down to, when we started with the meter side, it was, we looked at it, which product is reliable, which one has given us better longevity, who's got the better customer service when we have an issue, and what's the feedback. And, that was hands down Meter Group. And that's why we started working with Meter. And that was, and I say early on, it's not like it was that long ago on a calendar, but early on in the process, when we started this, that was just how we started working with Meter. Then internally, we started developing new reporting systems and started looking at, hey, maybe we can optimize what we do a little bit more if we could just make a few modifications. And that ended up leading from one conversation with Sean to, having an in-person meeting with Allison in Ohio. And then from there, it's like, hey, would it just be easier to get us all in the room and collaborate? And then we started getting in the room, and Meter put together a wonderful meeting with Dr. Campbell and an entire team of the brain trust there at Meter to say, hey, these were the people that helped define the science when it was created, 30, 40 years ago, and say, what are we getting right? What are we getting wrong? How can we improve it? And how can we keep staying on the cutting edge of this to where we're not just doing a test and giving you the results, but we're making sure that the tests that we're doing are giving us the most benefit, and we're able to get as much information out of as we can, which is a little bit of a unique crossover, because when Dr. Campbell did a lot of this science back in the day, it wasn't from a geotechnical and solar field analysis. It was from agriculture, and that transition is a little bit different than what we use in the geotechnical world. The science is still the same, but it was a great opportunity to understand where the crossovers were and how we were able to work together to find solutions to some difficult problems.
We knew our problem, which was, designing cables or designing, foundations, etc. And we had a good grasp of the problem. But the solution, which was understanding the thermal resistivity, conductivity of the soil, was beyond just measuring a data point. We wanted to understand the physics and science behind it, and therefore we needed a partner that goes beyond just providing the testing equipment, but a help for us to better define the problem and be able to find a consistent and representative solution for this problem. And Meter Group was the one that we were looking for because, as Matthew said, they went above and beyond the just being a provider of the measurement, but they helped us to understand the problem and also calibrate it for different conditions, specific conditions that we were dealing with, the different states of the soil, different sizes of the samples, different temperature, frozen, unfrozen, which all affect the measurement. And this is something that Meter was really helpful.
Speaking of that, both of you had come to give a presentation here at Meter Group a little bit ago, and you had mentioned this was one thing that I remember in your presentation, and this kind of fits in with what you're talking about with the new and kind of rudimentary measurements sometimes that you guys are doing. You were talking about thermal dryout curves, and I think had mentioned that there are some companies that might only do 2 points to create a tryout curve. What is your goal or hope for improving that process, improving the measurements that you get, and improving the outcomes that you have?
I would go beyond what you said. And, there's actually companies that some of our competitors that perform thermal testing to their clients, and they don't even provide 2 points, and they just give singular points. So anytime you have something new that has a lucrative financial benefit to it, people are going to take interest in it and sometimes delve into it with having more that they don't know than what they do know. And I think we kind of see that as an industry right now. If you went back 5 years and said, how many people do this test, you probably find 3 or 4. Now you find 15 or 20. So really, the question then becomes, who's actually giving you the most useful and accurate data? And it's not just about who's giving you data, but that dry out curve, as you mentioned, that's really where the value is for the electrical engineer that's going through and designing this system for whether it's data centers or for the solar fields. So as we go in and look at the data points we measure, to Arash's point, that we want to make sure we have a great understanding of the science behind it. And that understanding of the science behind it is what allows us to get the most accurate dry out curve. And sometimes that dry out curve doesn't exactly go through the data points, because anytime you take a single data point, um, you can have its deviation from what that dry out curve might actually look like. So instead of going and playing connect the dots, sometimes our curves might look a little bit off, but there's actually science backing the way our curves look.
The thermal resistivity is not a fixed property of the soil. It depends on the state of the soil. It depends on the moisture content of the soil, which that relationship is called that dry out curve. So previously, because sometimes maybe in old days, lack of alternative, people were measuring individual points at a fixed state of the soil or at a fixed moisture content, and they were extrapolating the behavior of the soil based on those limited measurements. Um, so it was kind of guessing, but sometimes a good guessing based on scientific methods and correlations. But Meter Group helped us to get out of that guessing business by providing us a continuous measurement of the soil at different state or at different moisture contents of the soil, which differentiates our measurements from groups out there that are still measuring individual data points and doing a line fit based on those measurements.
Is it a situation where you have like you said, a relatively new field? Is it a matter of just keep using, like if it ain't broke, don't fix it type of situation, and you keep using what has been traditionally used until that doesn't work anymore, and then you have to move on to something else? Or do you see it on the flip side where there's more innovation going on that you at Terracon or maybe other places as well, they're starting to look at pulling from these other new innovations? Arash, you mentioned AI, and that's especially huge in so many different industries and fields. I guess, can you talk a little bit about how that goes about when it comes to implementing new processes and instrumentation and all that?
Geomaterials are not man-made products, so it's all about how much we know about those materials. And if we don't have good ways of measuring things, or not knowing the exact mechanics or using rudimentary methods, etc., that means production of a lot of uncertainties in the process. And that uncertainty, if you don't know much about something, you try to be on the safe side, and therefore you add a lot of contingency risk safety factors to whatever you're doing, and eventually it works out. But that comes with a price of adding all these uncertainties. But as the science in this field grows and helps us to better understand the problem, then that means we are reducing that uncertainty, and therefore, while keeping us on the safe side, we can optimize our design. And that's a continuous path that we're walking on. We're still, designing things, but now with a higher confidence about what we know about the soil, and much more optimized design compared to what we were doing in the past. And therefore, Meter Group, and that example of the thermal resistivity continuous measurement rather than guessing, that means now we are more confident about our measurements, and therefore when we design cables, we are now having a much less risk associated with our design compared to what we were doing in the past.
I think as an industry, I don't want to say nobody else is innovating, because obviously I'm sure there are people that are out there, but there's also, for as many people as there are innovating, I'm sure there is also a handful of people that say, hey, keep the paychecks coming for this test, and we're just going to keep doing it the way we do it. I will tell you the direct quote from my boss here at Terracon, and it's the mentality of our senior leadership in the company. It's either we're going to do it and we're going to be experts at it, or we're not going to do it at all. We don't play in this game of we're going to be 1 foot in and 1 foot out. And I think that is part of what differentiates Terracon in this situation is we are making an investment because this doesn't come cheap. Whether it's just the time spent to learn this or the time and money spent to come travel to meter and have these meetings and to do all of that, there's a significant investment from Terracon to actually really take and understand this beyond, hey, here's a test. We know how to run the test. Here's your results. But to really, truly understand what we are doing. I think as a industry, one of the things that's unique about thermal testing is it goes beyond what we're familiar and used to as geotechnical engineers. This gets partially into thermodynamics, it gets into electrical engineering, and especially the electrical engineering side, a lot of civil engineers have never had a electrical engineering course. So understanding how resistance matters and all of that, and it's not, the electricity isn't flowing through the soil, the heat is. So that's getting into the thermodynamics. But how does the flow of the electricity directly correlate to the heat, and how all that works is, I think, it's something that creates a challenge where if you don't take a more holistic approach and understand that this isn't going to be covered in your soils mechanics textbook. The problems that we're facing are multidisciplinary, and understanding them takes a multidisciplinary approach to have a good understanding of the science. And I think if you don't take that approach to it, you're already a step behind with this. And as an industry, I think that's probably a foreign way of thinking about most of these problems.
Really quickly, what are the instruments that you're using there in the lab when it comes to thermal resistivity?
So we have two instruments we're using, the Varios meter and the Tempos. We use the Tempos for most of our testing. The Varios is effectively doing the same thing that the Tempos does, but it is creating the dry out curve for us in effect, in addition to just taking the readings. And it's what we're able to use it for is, it's a great device. Unfortunately, we don't have the size, the space to have 50 of these things laying out. So what we use it for is a kind of a calibration and a double check whenever we want to confirm something, or if we have a unique sample that requires a little more scrutiny, we'll throw it onto that Varios to get the complete dry out curve without us being engaged with it.
You mentioned some of the different. Well, actually, Matt, you mentioned at the beginning, and Arash as well, is that you have offices all over the country in the United States with varying soil characteristics at those different locations. Are there specific, I guess, emerging challenges? Arash, you also mentioned potentially dealing with frozen soils or frozen soils, or extremely dry soils or expansive soils. All those kinds of things. Are there specific challenges that you see coming up that require new ways of measuring or thinking about how to deal with those challenges?
That's a good question, and this field is keep changing, whether because of the external demand on coming up with new products, and like for example, geothermal systems being recent thing that they haven't been there a long time ago, or new structures, new equipments that are dealing with geotechnical properties of the soil. That puts us in a new position that we need to answer to those new questions by improving our understanding of the soil mechanic and also the way that we measure the soil. But also, yes, we have a lot of problematic soils or problematic situations that require special attention to those projects, like building a structure on top of a old mine or a karst or expansive soil or collapsible soil or soil that will be frozen or soil with a special mineralogy. These are new questions and new problems that we keep updating ourselves to be able to answer to those questions. And therefore, every time that we come across a new problem like that, we go back and revisit the way that we measure things so that we be able to understand to answer to that specific question, and we realize that okay, now we may need to improve the way that we test the soil, or we need to introduce a new measurement or a better way of measuring things so that we be able to provide a better answer for that problem. It's a ever-changing environment that we just keep improving these things constantly.
Without giving away any proprietary information, what's next for Terracon in terms of innovation and instrumentation? Are there new technologies that you're hoping to integrate? What do you think along those lines?
In short, we're really trying to work on our data collection and association, and using that to help us with a better understanding of how each material type reacts, and then understand that heat flow. We're taking a single data point and saying, hey, right at this area, this is what this value is. But it's looking at such a small area, it's not maybe capturing the entire flow. So one of the things that I hope to get farther along and get into confirmation after we do a little bit of theoretical work is saying, okay, if we go dig a trench, we know what the value of the trench is. Then how long does that value affect that heat flow? When does it get into the in situ material? When that in situ material has a different value, what happens to it from there? And trying to do some of that modeling to just help create more efficient designs for the electrical engineers that are out there.
Two other fronts that we're keep working on it, or at least I'm passionate about in Terracon we're working on, is one of them is about the massive amount of data that we have in Terracon. We have more than 2 million borings across the country. We keep adding more borings to it. I think 75,000 new borings every year. We have active 200 drill rigs that keep digging the soil and adding more measurements and more data to our historical databases. So, with that massive amount of data from different parts of the country on different aspects of geotechnical properties, we're trying to use them to first learn more about the fundamental correlations of different properties on each other. For example, on thermal resistivity, what are the other properties of the soil that are affecting this? And if we can have a better understanding of those parameters and the extent of their impact on this property, so connecting things together, and also being able to go on the uh, uh, instead of being reactive, being proactive on our designs and basically trying to better predict the properties way before we step a foot on the side, and be able to estimate properties of the soil for planning purposes and site selection purposes before doing the actual test on these materials. This is something that we are keep working on. We actually used our historical thermal resistivity database, and we digitized all those measurements and created a database of I think 18,000 data points across the US. And we worked on AI ML models to use those data and provide an estimation of the thermal resistivity for some of our clients that are looking to be able to estimate their cost of their projects for sizing the cables before necessarily starting the actual testing. The other thing is also historically, because as I said, because of all those uncertainties and also not being able to have a good measurements of the soil, we were heavily relying on soil mechanic that was based on certain assumptions about the state of the soil, fully dry or fully saturated, because they were the worst case scenario, and therefore our measurements were tied to that, and we were measuring properties under those extreme situations. But now with the advancements in our measurements, and also advancements in the unsaturated soil mechanic measurements that meter group is actually helping us to develop we are also working on that front, that we no longer need to assume for the worst case scenario, but we can measure the properties of the soil under different states of moisture content or loading conditions, or other states of the soil. So these two are the fields that we keep working on, so that we improve, on one hand, improve our understanding, and on the other hand, being able to provide some predictions of the behavior of the soil.
There will be those in our audience who are also doing geotechnical research of some kind, whether in the private sector or in academia, or the public sector or government agencies, other things like that. Do you have any final words of advice or learnings that you've had for those who are trying to scale their innovation or improve their processes, whether in field or lab work?
The one thing I would say to anyone who's innovating and trying to think outside the box is get outside the box. You're not going to change the box by staying inside of it. So go talk to people in different professions that are similar and try to find where things overlap and figure out the new path forward through there. Because if you stay in the environment you're in, you're never going to be able to change it from inside.
Yeah, and I would also add that geotechnical engineering is an interdisciplinary area that we can learn a lot from other branches of science, soil scientists or other branches of science. There are a lot to learn and implement in this field, so that's definitely a quick way to improve geotechnical engineering as a whole. The other thing is, for as a person who experienced academia and industry, I would say that it's better to get an insight of the real of the science, and being able to work on the things that matter and that can have a higher impact on the application. If you can get that idea early on from your research, that would significantly help you to come up with the solutions that would be widely used and be widely acknowledged in the field. That's going to boost the value of your research.
I think that's going to wrap it up for us today. Thank you again, Matt and Arash. We really appreciate you taking the time to come talk with us. It's been a really interesting discussion. So thank you again.
Thank you so much for having us. Looking forward to our partnership with Meter.
Absolutely. Thanks for having us.
And if you in the audience have any questions about this topic or want to hear more, feel free to contact us at metergroup.com or reach out to us on X at meter_ENV. And you can also view the full transcript from today in the podcast description. That's all for now. Stay safe, and we'll catch you next time on We Measure the World.